Okay, so I am going to give a lecture on the translation look-aside buffer. The translation look-aside buffer is right here, this slide deck. And on um, Tuesday the 20th, you will see a video that appears here, which is me going through this slide deck. All right, and with that, I am going to start on the translation look-aside buffer now. So, all right. So essentially what it's going to do is it's a fast cache that lives on the CPU. And its purpose is to cut down on all these excess memory lookups that you have to do to resolve an address. And we'll see how that works. So first thing that I'm going to do is I'm going to review paging. And then I want to talk about how we can make page translations a bit faster. And then what is the idea behind the TLB? Translation look-aside buffer to cache, where you save frequently looked up addresses on the CPU. So the CPU doesn't have to make a round trip from the CPU over the memory, over the bus to the memory space. So it dramatically speeds things up. It still has to do a virtual to physical mapping, but it's so much faster because it's done on the PC now. And it's so much faster that it makes the lookup time negligible. Let's see. I'll talk a little bit about what kind of workloads perform well with TLBs, and essentially they all do if your TLB is large enough. And how do TLBs interact when you have a context switch? A TLB is going to contain essentially virtual to physical mappings for a particular process. What happens when you switch to another process? Do you flush the TLB or do you somehow or another try to save the information? So let's start. We'll review paging. So here is a paging system, and I have two page tables that are in memory. And I'm going to start looking some stuff up. You can see that I'm assuming 4K pages, which means that I need 12 bits for the offset or 3 hex characters. I also want to know for process 2, I want to actually load that virtual address 0x000. Now what that is for process 2 is it is a virtual address. I've got to convert that from virtual to physical, which means I need to go to the page table and I need to read the first row. So the page table base register is pointing to the page table for process 2 right now. And I want to read the very first row in it, which is when I get there. So, but the page table is sitting at address 800. So the first memory access in order to actually load from virtual 000 is I've got to go to the page table and access the page table, which is at 0800. Now, if each row in the page table is 4 bytes long, then, well, it doesn't matter at this point because I'm accessing the first row. So I just go to 800 and I read at 800. And then 800, and when I do the address translation, it says that my virtual page 00 is at a physical page 6000. And so when I do my address translation, it's 6000 plus 000, which is the offset to give me my physical, which gives me my physical address. Now that's 2 memory accesses now, one to read the page table and one to actually read from location 6000, physical location 6000. So for process 2, I'm still with process 2. The page base register is still pointing to process 2's page table. And I want to load from 0x1444. Now the offset into the page table is 1. So that means I go to process 2's page table, which is at location 800, and I go to the second row. Now the second row, I need to know how long each row is. Now, if I'm assuming that each row has 8 bytes, it's a 64-bit system, then the second row on that page table is going to be at location 8000 plus 8, or 8008. And I read that row from memory to get the virtual to physical lookup for so I can map virtual page 1 to its actual physical page, which is at location 2000. And then I add 0x2000, the physical page for associated with virtual page 1 for process 2, and then I add the offset to it, which is 444. So my virtual to physical lookup requires two memory lookups, one to the page table and one to the physical page. My virtual address of 1444 is translated to a physical address of 2444, but now I need two memory lookups. Now, if I switch to process 1, and I want to read from process 1, I'm going to read from the very same address, 0x1444, but it's a virtual address. All processes can be reading from the same address, but the page table will map that virtual address to some physical address, which is unique to that particular process. So the page table base register is now pointing to memory address 0. So I go to memory address 0, and I add the size of one row to get to the second row in P1's page table. So I'm loading from 0008, and then I see that my virtual address 1 maps to a physical address of 0x5000. So I take 0x5000 and I add the offset of 444 to 5000 to get the physical address of 0x5444. Notice that process 1 and process 2 are both loading from virtual address 0x1444, but process 2's, the actual physical address for process 2 is at physical address 2444, and the physical address for process 1 is at process 1's virtual address of 1444 is at physical address 5444. So if each page table entry weren't 8 bytes, if it were just 4 bytes, then all that would change is these offsets here when I'm indexing into my page tables. All right, so paging pros and cons. One of the advantages is there's no longer any external fragmentation. And all free pages are equivalent, and it's super easy to manage those free pages. The OS can use just a list. It's a big O of 1 to find memory. Processes can grow without having to be recopied. It's lots of awesomeness associated with page tables, but there are huge disadvantages. One is page tables are huge. So if I have a 32-bit system with 12 bits of offset, then my page table has 1 million rows, and each row is 4 bytes long. So my page table will take up 4 megs. And the only array requirement for my operating system is that the page table is in contiguous memory. Any other array can be split across any number of pages, but the page table cannot. So we got to fix that. And the page table is just too big. So for a 100K process, you have a 4 million byte page table. It's ridiculous. We'll fix it. Another advantage, a big advantage, is a page table is going to double the number of memory references per instruction. One to go look up the virtual to physical mapping in the page table, and one to actually go to the physical memory location that you want. All right, so the translation steps using page tables. You've got to extract the virtual page number from the virtual address first. Then you're going to calculate the address of the page table entry, which is where you need to go in the page table, which is the page table base register plus the virtual page number that indexes you into the page table. And then you've got to read the page table entry from memory. So you go to memory and you read what the physical page mapping is. Then you're going to extract the physical page from memory, which is step 4, build the physical address, and read the contents of the physical address. Now, some of these steps are expensive. 3 and 6. That's because you're reading from memory. Now, the one that we can speed up today is not 6 because we're reading from memory for the program that we're running. The one we can speed up is 3 because it turns out if we're reading from the page table, we're going to read the same entries over and over and over again. So this is the one that we're going to speed up today, step 3. All right. And so let me give you an example of how this would operate. So I've got this, hold on a sec. Google Meet is trying to kick me out of the call. Am I here? I guess I am here. All right. So I want to do an array iteration. So And I've got this array that I'm iterating over. And I'm going to assume that A here, A there, starts at address 3000. And I've got this page table down here. And that's my virtual address. That's where it starts. And I can map that virtual here to a physical page of 7000. So my virtual address is, I'll start at 3000. And if I'm iterating over A, if it's an integer, then it's, I'm going to go from 3000, then 3004, then 3008, then 3012. I'm always in the same page. And I'm in the same page for, I stay in the same page for the entire size of that page, which is, in this case, it looks like it's 3 hex characters, which is 3 times 4 is 12 binary characters, which is 4K, which means in 4 kilobytes will hold 1,000 integers. So what this is saying is if I'm iterating over this array, I'm going to go to that 4th row in the page table 1,000 times and read the same thing. Virtual page 3 maps to physical page 7,000. Excuse me. All right. So I'm going to first start by loading from location 3000, and then I load from location 3004, and then 3008, and on and on and on. The physical addresses from 3000, I've got to actually go to the page table, load my page table. My page table starts at 1000, and the 4th row where I'm mapping the 3rd virtual page is at location 1000C. So over here, you can see that now I've got repeated access to this particular memory location. Read that location, do the virtual 3 to physical 7. Same again, same again, same again. I do this over and over and over again. And why do that? Why not just cache that information and save it for later? Do it once and then save the information for later. And if you can figure out how to do this so that it's fast, then you pay a pretty heavy penalty the first time you go to this page. But from then on, you've got these fast accesses. And that is the main idea behind translation look-aside buffers. And let's see, from what you can infer from this, well, the page table base register in this case is going to be pointing to 1000 because that's the page table that we're operating in. The page table is going to have each row has 4 bytes each. And you can tell that because I'm incrementing 1000, 1004, and 1008. That means it's a 32-bit system. Virtual page 3 maps to physical page 7. And you have 12 bits of offset because you have these extra 1, 2, 3 hex characters, which is 3 times 4 is 12. And you have this additional 4 bits. Well, I don't know if it's 4 bits here. This 3 hex character, I don't know how high it goes. Right now, if 3 is the max that I have, then this could just be 2 bits, which would let me go up to virtual pages 0 through 3. But the main takeaway is when I'm using a page table, I constantly go to the same place over and over again. So here's what you do. You just put a little cache on the CPU. And you cache frequently looked up stuff that you see all the time. So if you do that, then you avoid the first time you encounter a virtual page, you have to go over this bus to the memory to actually get the virtual to physical page mapping. But then you save it in the cache. The next time you try to do that virtual to physical mapping, you find it here. And if this cache is 1,000 times faster than this RAM, or if you can make it so much faster, then the access effectively disappears, then you effectively drop from 2 accesses per page to 1 access if the cache can be fast enough, if your hit rate is fast enough. And it's on the CPU. It's right next to the registers. It's accessed at register speed. So yeah, it is much, much, much faster than going over the bus to get to the RAM. All right, so if I'm going to iterate over this array, I have 2040. Apparently, I've got 2048 entries in this array of ints. So that an int is 4 bytes long. So 2048 times 4 is that this array is going to take up 8 kilobytes, which means that if I have 4K pages, this array is going to take up a minimum of 2 and a maximum of 3 pages, and that depends on how it's aligned to the page. If the array starts at a page, then it can take up 2 pages. It will only take up 2 pages. If the array, however, starts in the middle of a page, then it's going to take up the rest of that page plus a whole other block plus part of another block. And that's how it would take up 3 pages. All right. So if I'm going to use a TLB with this, let me show you what the behavior would look like. So you start off, first off, you need a TLB. And here's my representation of a TLB down here. I've got this valid bit because it's a these bits, virtual page number, there's going to be some bits here no matter what. I need some way to indicate whether it's a valid mapping. I start off with, here's my page table base registers pointing here. And here's what my page table is. Virtual page 0 maps to physical page 1, 1 to 5, and so on. And so if I'm going to start off by accessing virtual page 0x100, that's virtual page 1. What I have to do is this. I have to load the first entry in this page table. The page table starts at 0, so I have to load the second entry. I'm sorry, this entry here. So I go to 004, this entry here, and I'm at my virtual page of 1 to physical page of 5. And I saved that. Hey, virtual page 1 maps to physical page 5, and I got a valid here, and all the other entries apparently are I should have invalids here or zeros. And then I keep going. So now I can map this virtual address of 1,000 to a physical address of 5,000. And then I go and get the next entry in my array, 1,004. I go to my page table and I get the first entry right here. But it's a little bit different now. So what's going to happen is the way that this works is whenever I do a page lookup, the first place I look is I look in the CPU's TLB to see if there's a valid virtual to physical mapping for what I'm after. If it's not there, I go to the page table. So let me start over with this again. So my TLB has nothing in it. I go to virtual address 1,000. I first check the TLB. Hey, is there a mapper from 1 to something? No, there's not. All right, then I have to go out to my memory and actually get this mapping. So that's one load from memory. And then I save that mapping 1 to 5. And then I actually go to the physical address and load from the physical address that I want. The next access is I want to load from 0x1004. Well, I've got to go to my page table again. So the first thing I do is I check, hey, is there an entry in my TLB for this? Yes, there is. Virtual page 1 maps to 5. I don't have to go out to memory. So that's called a TLB hit. And in fact, it's much faster than a memory access. So I'm going to assume, and it's close to negligible time. But then I've got to, once I do the address translation, virtual to physical, I've got an address of 5,000. I've got to go out and read this from my memory space. And I just keep going. I get TLB hits on and on until I step into a page that is not in the TLB. So I read this whole page, and eventually I step into the second page. Now I'm going to load from virtual page 2. I see if there's a entry in my TLB for virtual page 2. There's not. All right, now I have to go to my page table. Go to my page table, add 2 times the size of an int to 0 to get to the entry that I want, which is load from 008. That gets my virtual to physical mapping of 2 to 4. I save that in my TLB, and then I've got my 2 maps to 4. So that this location virtual 0x2000 maps to 0x4000. And then I go and load from the very next integer, 0x2004. The first thing I do, check the TLB. Is there a mapping for virtual page 2? Yes, and it's valid, 2 to 4. I don't have to go to memory. So I just directly build my physical address because I have a TLB hit, and I go from 4004. Go to 4004 directly. So the performance of a TLB is kind of interesting. I've got this, I have this array again, and I'm going to access 2048 integers. So this array is going to take up basically 2 pages. It will take up 2 pages if it aligns within the page, or 3 pages if it doesn't. So I'm just going to assume 2. I'm going to assume that it aligns within a page. So I want to figure out what the hit rate is now and the miss rate. So the miss rate is the number of misses over the total number of TLB lookups. So number of TLB lookups, well, I have 2,048 integers that I'm actually going to access in my memory. So I have 2,048 lookups. My number of misses, well, it depends on how this is aligned. If this array of 2,048 integers happens to be aligned within the pages just so, then it can fit within 2 pages, which means I'm only going to have 2 misses because I have to go to 2 unique pages. So, which gives me a miss rate, number of misses of 2, which gives me a miss rate of 2 over 2048, which is 0.1%. And the hit rate, of course, is 1 minus the miss rate, which is 99.9%. So this looks pretty good. So TLBs give you this sort of thing. They virtually eliminate the page table lookup penalty that you have to pay using page tables. And that gets rid of one of the big problems with page tables. It doesn't handle the size of the page tables, but it does handle the double the memory lookup problem. Here's a question. Would the hit rate get better or worse with smaller pages? If you have smaller pages, then what happens is you have to access more pages. With 4K pages, 8,000 bytes will fit in 2 4K pages. If I was using 2K pages, then I would need 4 2K pages to fit that array, which means the number of misses that I have would double from 2 to 4, and my miss rate would get worse. My hit rate would get a little worse. Not much. It would, instead of 2 over 2048, it'd be 4 over 2048. So, and it's because you'd have to access more pages. So in terms of TLB performance, this brings you to this. How can you improve it? Because translation look-aside buffer lives on a CPU, and that real estate's precious. So you can't just grow your TLB and make it larger and larger and larger. In fact, the larger it is, the slower it has to be, because the larger it is, the more real estate it has to take up, which means some of that real estate is going to be further from the actual ALU, and you have to determine the speed of the translation look-aside buffer based on how long it takes to get to the furthest part of the TLU. So the larger your TLB is, the slower the access is. It's not much, but it's a little bit. And plus, you're doing a whole lot of there's a lot of other the transistors in the CPU. There's a lot of other stuff going on in the CPU. So your TLB can only be but so large. What you can do to increase its performance is, well, you can increase your page size. So for the problem I had before, if I increased my page size from 4K to 8K, then that array would fit in 1 page. And my miss rate would go from 2 over 2048 to 1 over 2048, which means my hit rate is just that much better. And this brings up another term. It's called TLB reach. That's the amount of memory that a TLB translation look-aside buffer will cover. And it's the number of entries in a TLB times the size of a page, which will tell you the amount of memory that a TLB will cover. It's called the TLB reach. So there are various workloads that you can study and see how the TLB performs. And it turns out that it's going to perform well as long as the TLB is large enough. If it's large enough, it'll perform well on all workloads. If it's not large enough, you'll run into some problems. All right, so we'll start with there are 2 that I want to consider: a sequential array access. So those are going to perform well because your hits are almost always within the same page. Super fast. Now, if you have a super random access pattern where you're accessing memory in a random way, that has the potential to perform poorly. But if your TLB is large enough, it will also perform well because you just keep adding TLB entries, and eventually you have a TLB entry for all of these random pages you're accessing. And from that point on, you get TLB hits. But it depends on if your TLB is large enough. So let me give you some access patterns. So I have this workload, 2 access patterns. The first one on the left is a sequential access pattern where I sequentially iterate over this array. The second one is a random access pattern. But as long as your TLB has more than 2 rows in it, both of these are going to perform about the same. So the first access pattern is I keep getting a hit over and over and over again in the same place until I go to a different page. And then I get a TLB miss, and then from then on I have TLB hits. The second access pattern is you have random accesses to different places in memory. You just, what you do with the second access pattern, which is randomly accessing memory, is you're going to populate your TLB faster with that one. And as long as your TLB is big enough, the second access pattern is going to perform basically about the same as the first access pattern, as long as it's big enough. So these are 2 kinds of locality. Didn't I mention the spatial locality? The concept is future accesses are to, if you're accessing an address at, say, location 100, you're probably going to access location 104 next. That's what spatial locality is. Temporal locality is you're accessing location 100 right now. Sometime in the future, you're probably going to come back and access locations around here anyway. And so both of these kind of lend themselves to a TLB. So for spatial locality, you're accessing the same page repeatedly. So you need the same virtual page to physical page translation over and over and over again. So basically, you populate your TLB once, and then you get TLB hit after TLB hit. For temporal locality, you're going to access the same address in the near future. As long as you access a page now, you save it in TLB, you go somewhere, a bunch of other random pages, and while you're going to these random pages, you keep adding to the TLB, and eventually your TLB will be full, will have entries for most of the pages you're accessing, and your hit rate will start to go up. So for temporal locality, it's going to work okay, pretty well. It's going to work well too, as long as it's big enough. All right, so there are a couple of replacement policies you can use, and here's where the TLB falls apart. You can have a least recently, because what happens with the TLB is what happens when you do fill it up. So if your TLB holds 6 entries and you have a 7th unique page, what do? There are 2 kinds of replacement policies. You can kick out the oldest entry in your translation look-aside buffer, or you can randomly evict one of your entries. Now, it turns out that you can have some troubles here. So I've got this TLB on the right, this thing over here. It's a TLB that holds 4 entries, but I have this memory access pattern that accesses 5 separate pages. So if I'm going to repeatedly access these pages in the same order, what's going to happen is I'm going to get a hit rate of 0, because I'm going to I'll loop like this. I'll access location 0 and then 1 and then 2, virtual page 0, 1, 2, 3, 4. What's going to happen is I'll start here and I'll have 0 to 3 and then 1 to 4 and then 2 to 5 and then 3 to 6. And when I get to here, when I get to this last one here, accessing the 4th page, 4 to 7, my TLB is full. If I'm using the least recently used policy, I'm going to go to the entry in my TLB that was used the furthest to go, longest to go, which is this one. And I'm going to delete it and replace that with 7. And then the very next access that I have is I want to access virtual page 0. I just replaced virtual page 0. And I replaced it with this mapping, 4 to 7. And so what will happen in this case is I'm going to have 5 TLB lookups. I'm going to have 0 hits, and my hit rate is going to be 0 out of 5. And if I keep doing this workload, following this workload, where I'm accessing 5 pages repeatedly, where my TLB only holds 4 entries, and what's going to happen is I'm going to get a hit rate of 0. So this is where least recently used kind of falls apart. And least recently used is going to require some hardware to implement it. Whereas if you used a random policy, randomly replace an entry in the TLB whenever you run out of space, you're not going to have this issue. So sometimes a random policy is better than a smart policy. All right, so what's going to happen when you switch processes? You are running your process, it's accessing a lot of pages, and then you switch to another process. Do you flush the TLB? Well, that was kind of expensive to build. So do you flush the TLB or do you kind of track it? Well, if you make your TLB a little larger, then you can hold translation look-aside buffer entries for multiple processes. Now, this is going to require you to have core affinity. Actually, it doesn't, because the TLB is separate from the cores. So you just have a TLB that's shared with the cores. And that way, the TLB can be, well, if you switch from process 1 to 2, then just save process 1's TLB entries. But what this is going to require you to do is have an additional field in the TLB, a field that's going to track what process a TLB is associated with. And you do this with, well, you could use process IDs, but process IDs are 32 bits long, which means that if I had an ACID, if my TLB had this additional identifier of a process ID, that's 32 more bits per line, which implies that I can have 2 to the 32nd unique processes, which implies that my TLB can hold virtual to physical mappings for 4 billion processes. And it's just not that big. It's going to hold, at most, it'll hold a few thousand virtual to physical mappings. So the reason why use something called an ACID, which is a process identifier, which is much smaller. It's only got 8 bits, which means the TLB can hold up to 2 to the 8th or 256 unique processes. And so now my TLB can, whenever I pay the huge cost of going to do a virtual to physical lookup, when I save that lookup in the TLB, I'm not going to use it. I'm not going to lose that information when I switch processes. And so here's how this will look. Notice my TLB down here now has an ACID, which is tracking the processes, and it's also got a valid bit. So if my page table base register is pointing here, that means I'm in this process. I'm using this particular page table. So if I'm going to load from 0x144 with an ACID of 12, the first thing I'm going to do is I'm going to look to see for the ACID of 12, do I have a valid virtual to physical mapping for virtual page 1? There's 12. This is valid. Yes, 1 to 2. I get a TLB hit, and I can direct, let's see, load. Where's that? A TLB hit, and I load from 244. So now if I switch processes, and I'm at this process now, and if I'm trying to load from 0x1444, same address, but for ACID 11, first thing I do is I look down at my TLB. For ACID 11, do I have a valid mapping from virtual page 1? That's not valid. That's valid. So I've got a valid entry for ACID 11 that maps virtual page 1 to 5. So now I can directly build my physical address. So that's how a TLB would work. So the TLB performance, it turns out that the context switches are pretty expensive, and you don't want to lose your TLBs. And even with the ACID, other processes are going to wind up polluting the TLBs. What are you supposed to do? Because if you have several hundred processes running it, well, I have 400 processes running on my machine. And if my ACID would only track 256 processes, I am still not going to be able to keep track of all of them in the TLBs. What you can do is have multiple TLBs on your processor, one for data, one for instructions. And that way you can, in the one for instructions, it's probably going to be, well, if you're accessing data, it's probably going to be sequential. If you're accessing instructions, it's probably going to be sequential. You can have multiple TLBs to try to track, is to hold on to this virtual to physical mapping for as long as possible. So you can boost your performance and not have to re-look up something again and again. You don't want to have to repeat yourself. So what's going to happen when you get a TLB miss? There are 2 ways to do it. You can have the hardware that does it or the operating system that does it. If the hardware does it, then that makes for a more complex hardware system. The CPU has to know where the page tables are. And no worries. You have a register in the x86 architecture that'll track it. The page table structure is also going to have to be fixed, and it has to be agreed upon by the hardware and the OS. You can do that too. And then what will happen is the hardware will walk the page table and fill the TLB even before you're running these processes. So it can fill the TLB beforehand. All right, so that's nice. Or you can have the operating system. So with hardware, you can pre-allocate TLB entries, and you can do it fast. If it's in software, it's a little slower, but it's more flexible. So what will happen is when you get a TLB miss, you'll trap into the operating system for a TLB miss. And this is a software managed TLB. And what's going to happen is, well, the OS has got to be able to interpret the page table, however it chooses, and it's going to modify the TLB entries when it has a page miss. You can also have protection bits on the TLB. Same protection bits on the TLB as in a page table. So you can have TLB can have protection bits. It can have an ACID, and it also has the virtual to physical mappings. And you want it to be as big as possible. And so to summarize, these paging is great, but accessing page tables for every memory access is going to be super slow. No worries. You create this cache called a TLB that will hold on to the recent virtual to physical mappings. And this is going to dramatically improve your memory access speed. It's going to mostly eliminate that page table lookup as long as your TLB is large enough. Your TLB performance is going to depend strongly on workload. So sequential workloads are going to perform well. Workloads with temporal locality can perform well as long as the TLB is large enough. And you can increase the TLB reach, the amount of memory that it will cover, by just increasing your page size. You go from 4K pages to 8K pages, go from 12 bits to 13 bits. Different systems, you can have different systems. You can manage the TLB using the OS or hardware. And the TLBs themselves are going to increase the cost of context switches. What do? You don't want to flush the TLB. So you want to save as much of the translation look-aside buffer entries, information for every process that's running when you're switching processes, because when you come back to that process, those entries are still going to be valid. But that requires you to have a larger TLB, and it requires you to have one more step, which is making sure that the ACID for the process, or making sure that the process that's currently accessing the TLB, making sure its ACID is in the TLB. So it essentially adds a requirement to the TLB that it's large enough to hold a typical number of processes and a typical number of processes pages. So your TLB has to grow dramatically if you want to save TLB information across context switches. And that's it. That's all for TLBs. All they are is basically just this fast cache that lives on the CPU that pretty much eliminates the cost of the virtual to physical page lookup. And with that, I will see you guys when I see you. Bye now.